This is problem 84 from chapter 13. The 2-pound block is released from rest at A and slides down along the smooth cylindrical surface. If the attached spring has a stiffness of 2 pounds per foot, determine its unstretched length so that it does not allow the block to leave the surface until theta is equal to 60 degrees. So we have the angle theta here. We have the spring constant K, we have the weight of the block is released from rest, so the velocity at point A is 0, and we're looking for L naught, which is the unstretched length of the spring. So the first thing we want to do is determine the tangential direction and the normal direction. I'm going to look at the block when it's at an angle theta. So the tangential direction was the direction that the block is going in, and the normal direction is in towards the center of the circle. Now I want to look at the forces which are acting on the object. So I have the tangential direction and the normal direction. I have the force of gravity acting downward. I have a normal force which is perpendicular to the surface of contact. I have no frictional force because the surface is smooth. And I have the force of the spring acting inwards. Let's call this Fs. And this angle here is theta, which means this angle here is theta, which means that angle is theta also. I have to break the force of gravity into normal and tangential components. So I have normal force here, force of spring here. This is the sine component for the force of gravity, and I have a cosine component. Okay, so now I look at my equation sheet. For Newton's second law, I have the normal direction and the tangential direction. In the normal direction, I have the sum of the forces is equal to the mass times the acceleration in the normal direction, which is v squared over rho. And in the tangential direction, the sum of the forces is equal to the mass times v dot, which is the tangential component of the acceleration. So in the tangential direction, I just have one force, so I have mg sine theta is equal to m times v dot, therefore v dot is equal to g sine theta. Now let's look in the normal direction. So pointing inwards, I have mg cosine theta plus the force of the spring, and perhaps you have written on your equation sheet that the force of the spring is equal to K times S, and I think it's helpful to say the magnitude for the force of the spring is equal to K times the absolute value of S, and that's equal to K times L minus L naught. We're looking for L naught. The problem here, if you don't use the absolute value sign, is that S could be negative, which would change the direction of your force, but we already know that the force is pointing inward. Okay, so K times the absolute value of S minus N is equal to mv squared over rho. And I know that at 60 degrees, the block is going to leave the surface. So at theta equal to 60 degrees, n is equal to 0. So I have mg cosine of 60 degrees plus k times the absolute value of s is equal to mv squared over rho. Okay, now I know m times g is 2 pounds, so this is 2 times cosine of 60 degrees. I know k is 2 pounds per foot, so this is 2 times the absolute value of s is equal to m, which is 2 divided by 32.2, since m times g is equal to 2 pounds. And I do not know v, and rho is equal to 2 feet. I'm looking for S because if I can find S, I can find L naught, but the problem here is that I need V when theta is equal to 60 degrees, and all I know is that when the block is released, the velocity is 0. But I can use what I have here from looking in the tangential direction, and going back to my equation sheet, I have equation 1219, which says the tangential component of the acceleration integrated with respect to ds is equal to the integral of v dv, and the tangential component of the acceleration is v dot. We can see that from this equation here. And remember that this S has to do with the current length of the string and the unstretched length of the spring and the difference between them, whereas this S is the distance that the block travels, so those S's are not necessarily related, which is why sometimes I suggest just using this with L minus L naught instead of the S, because it can make your life more confusing than it needs to be. Okay, so at point A, the velocity is 0, and we'll say at that point S is equal to 0. Sometime later, we're at, let's just say S and V. So I can integrate, if I put in g sine theta for the tangential component, I can take care of the integral on the right hand side, so that would just give me 1/2 v squared. Now I'm in a little bit of trouble because I have a theta here, and theta depends on S, but I can't integrate with respect to S the way I have things now. But remember that ds is a small piece here, and, well, maybe I should draw it like this. Okay, so that's a small segment of the arc length, and the radius is, well, 2 feet, but let's just call it rho, and this would be a small angle d theta. So by the arc length formula, ds is equal to rho d theta. So I can put that in for the ds, and then I can integrate. So I have g sine theta rho d theta. The g and the rho can come outside. My limits of integration are going to change, so I'm going from 0 to 60 degrees. And this is equal to 1/2 v squared, where that will be the velocity at 60 degrees, which is what we're looking for. Okay, so I have g rho, I integrate sine theta, and I get negative cosine theta, and I plug in my limits of integration, and I have negative cosine theta of 60 degrees plus cosine of 0 degrees, and that's equal to 1/2 times v squared. G is equal to 32.2, rho is equal to 2, and cosine of 60 degrees is 1/2, but it's negative, and cosine of 0 is equal to 1. And you can solve this to find the velocity at 60 degrees is equal to the square root of 32.2 times 2, which is the square root of g times rho, which is just kind of interesting because we've seen that before. Okay, so now going back to the equation that we have here, I have 2 times cosine of 60 degrees plus 2 times the absolute value of s is equal to, this would be v squared divided by g, right? Let's actually use this for v, so v squared would be equal to g times rho divided by, this was g, so that actually cancels out, and this is just rho, which is 2. Oh, well, that was kind of confusing. Just ignore that there. So that would just be equal to 1. So this is cosine of 60 degrees plus the absolute value of s. is equal to 1, so the absolute value of S is equal to 1 minus cosine of 60 degrees. So the absolute value of L minus L naught is equal to 1 minus cosine of 60 degrees. Cosine of 60 degrees is 1/2, so that's 1 minus 1/2, which is equal to 1/2, which has units of feet, so that's half a foot. Now, the current length of the spring is 2 feet, and the spring is stretched. So the unstretched length is half a foot different than 2 feet, and since the spring is stretched, the unstretched length should be smaller. So this is L minus, let's just say 0.5 feet, and L, you can see, is going to be the same as the radius, that's the radius of curvature. So this is 2 feet minus 0.5 feet, so the unstretched length of the spring is 1.5 feet because the spring is stretched by half a foot to its current length of 2 feet. And that concludes problem 84.